Fantastic. What we're going to do is we're going to go over a sample circuit. I do not expect you to understand the workings of this yet. Just give you a sample circuit, what goes in and what comes out. And then as we go from chapter to chapter to chapter, there's going to be more detailed explanation of how this circuit works. Just to give you an idea of a typical electronic circuit specifically. Now what this is this is showing you a specific situation where we're coming in from the antenna, going through a bandpass filter. Now this is actually a radio, what they call a super heterodyne radio. And that goes here. You'll notice that this is the symbol for an antenna, right there. That's one of them. There's several different symbols that you can have for an antenna, okay? Right here is a bandpass filter, and a bandpass filter is a tunable filter that will select the radio station you want. Notice this symbol right here? That's a symbol for a capacitor. So some of the things I'll do is explain what they are, and then we'll go into the details of how they work later. This right here is a symbol for an inductor. And see the arrow that's going through it? That means it's adjustable. So you're able to adjust that to be able to pick up the particular frequency that you want on the radio waves. And the next stage is what they call an RF amplifier. RF amplifier stands for radio frequency amplifier. Okay? And what it does is it's a broadband amplifier that will boost the signal up. Because when the signal comes to your antenna, this down here may be a microvolt or 2 microvolts, if that much. And so that selects the particular antenna, and then this boosts the signal up to give you what they call a better signal-to-noise ratio. We want our signal to be very, very much larger than the noise that exists in the circuits. When we talk specifically about the RF amplifier in a few days, we'll actually see how that works on that. The next stage that it goes through is the RF amplifier. You'll notice this symbol right here. See, it looks like a little comb. That comb is what they call circuit ground or circuit common. And we'll see about 3 different symbols they use for ground, and this is one of the problems when you get into testing. Have you ever heard the term ground loops? It's a ground loop problem. We'll talk more about that specifically, but the ground loops are a big problem when it comes to testing. And one of the reasons is they're not consistent in what they mean by ground. Now, if this is a capacitor and a resistor, and this symbol right here is a diode. See how it has that little arrow with a dash right there? That's a diode. The diode allows current flow in one direction. So it blocks it another direction, allows only one direction. And right here is a little transistor specifically that amplifies the signal. Then it goes into what we call a transformer. See the transformer right there? Notice that there's 2 coils with 2 bars in the middle. That's the schematic symbol for a iron core transformer. Iron core is used at lower frequencies. Typically, we consider low frequency from about a megahertz down. And we're dealing in the radio signals, which would be effectively what we're looking at, is going to be the audio we're looking at is 20 hertz to about 20 kilohertz, which is in the audio range. So we'll be working with iron core transfers in that thing. And then right here, you'll see a signal coming into it. And what happens is back here, it'll sample a signal as far as the volume, and it'll try to keep the volume out consistent from station to station, also when you're traveling like in a radio in a car. And that'll feed back energy to increase the signal when it gets weaker or decrease the signal when it gets stronger so your volume is constant. We'll go through that in more detail too. Right here, the RF signal comes up to what we call a mixer. Mixer is a circuit that will take 2 signals, mix them together to produce the sum and the difference. So there's 4 signals there, 4 of them, okay? And you actually select, the system selects the smallest or the lowest frequency because it's easier to work with low frequencies. So it picks that through the use of this low-pass filter. See that? It's called a low-pass filter. Now you'll learn how the capacitor works and how the inductor works later on today, specifically to be able to select the low frequencies and reject the higher frequencies. Then what happens here is that when we selected the lower frequencies, we'll use what they call an audio preamplifier. That'll boost the audio signal up thing you're trying to listen to. Then it goes through a series of different types of filters, low pass, high pass, low pass filters. I want you to notice something here. See this low pass filter here? That's using resistors, capacitors, and inductors. Those are what we call passive components. They don't require an electrical signal to work as far as, a bias voltage. So these are called essentially passive filters, but over here, you'll notice there's a special little circuit called an operational amplifier. See the shape of this amplifier? Sometimes it's just down, straight, or curved, but you see the plus and the minus here? See the plus right there on that input and the minus there? That tells you that it's an operational amplifier. An operational amplifier is a very special little device. I call it the Old Bay of electronics. Have you ever seen Old Bay seasonings, guys? Yeah. Yeah. You ever read the can, Don? No. Or Dan? But if you take time to read the can, it says it does meat, it does fish, it does pork, it does popcorn, it does vegetables, it does salad, so it does everything, right? So that's what I mean by the operational amplifier being the Old Bay of electronics, because it can be made to do anything. It's a very, very versatile electronic tool. And it goes on through here, and then what we do is we come back over here, and you see the audio amp. The audio amplifier takes the 20 hertz to the 20 kilohertz, boosts it up, impedes matches to the speaker, and out comes the music. Of course, today we're not using speakers as much as our earphones, are we? So this kind of gives you an idea, and if you take a look at the different components, we'll look at some of the different values. Up here is the fixed value resistor. See, it's just basically a squiggly thing. So you can tell by looking at that component that it's a resistor. Resistor is going to resist the current flow. Right here is a fixed value capacitor. I'd like to point out, you can't see it as well here, but that top bar is straight, and the bottom bar is a little curved. That designates a capacitor. The main reason for that is that switching circuits use two bars. They're straight, and you can get confusion. And originally, it used to be the capacitor was two bars. Then they realized there was too much confusion between the switch circuits and electronic circuits, so they made it that way as far as that goes. Notice here, that says that's a ground connection. Well, that's a circuit ground, and you'll actually see another ground as we bring it up later on. That's one of the symbols for an antenna. Sometimes you'll see a bar across the top. And this right here is a transistor. In this case here, it's an NPN, and we'll learn how that construction works. We talk about the construction of a transistor and how it amplifies. This right here is a junction FET. FET being field effect transistor. Now, the purpose of a field effect transistor, which we'll go through the theory of later on, is to have what they call a high input impedance. You'll learn how when you need a high input impedance, you're not loading the circuit down, which means you're not changing the voltage values. You hook a meter around. Again, there's the inductor, and that's with a little arrow through it called adjustable inductance. Here's an operational amplifier. What can you tell about an operational amplifier? What is it that tells you that it's an operational amplifier? Plus and minus, absolutely. But depending on the circuit you hook up, the plus will be hooked certain ways, and the minus will be hooked certain ways. We cover that, probably the third day. In the third day, or the last part of effectively the third day, specifically on that. And again, here's a diode rectifier. This is a transformer. What can you tell about this? What kind of transformer is this? Iron core. That's right. Iron core is used at what? High or low frequencies? Correct. Low frequencies. Typically, you'll see 20 hertz to 20 kilohertz, but we consider 1 megahertz and down as low frequency. And consider like 10 megahertz and above as high frequencies. This is a transformer. This is an inductor. Notice it says iron core inductor. Its purpose is to basically oppose current changes. That's the purpose of an inductor, is to actually oppose or enhance current changes. RF stands for radio frequency. AGC is automatic contained control. And then you have CW, that's continuous wave. SSB, single sideband. When you take and you actually mix the signals together, remember that? You had the two original frequencies, and you got the sum and the differences. The sum signal and the difference signal are called sideband frequencies. And the SSB means I'm going to get one of those sidebands. It usually selects the lower frequency. Now, this is going through a little more explanation of what we did. We'll be able to go through this probably a little faster than we did before. And what we're saying is the circuit diagram consists of passive filter circuit, one tuned circuit, 3 active filter circuits, 3 op amps, 2 amplifiers that use transistors, 1 amplifier that uses FET, resistor, capacitor, inductor circuit components. Now, this is what they call a block diagram. You notice that block diagram doesn't show you any components, does it? It's just like a general description is what it is. And many times you don't even see a schematic diagram anymore. You'll see a block diagram. And notice here's the signal from the antenna. Here's the band pass filter. That's selecting the particular frequency one. Here's the RF amplifier. Here's an automatic gain control signal that's taking feedback, combining it, then going into the mixer. That's a typical symbol you'll see for a mixer. This is the B frequency oscillator. That's the oscillator that's going to take and provide the signal that allows you to get the sum and the different signals. Here's a low pass filter, audio preamplifier, high pass, low pass, and it goes into this level here. By the way, you should probably, okay, that would be a connection. And it goes into the audio amplifier, which is the speaker, and then also it samples that signal and goes back here and allows it to adjust either plus or minus to allow the signal to stay consistent in the speaker. I don't know if you've noticed this or not, but some of the older analog radios, you could take and adjust it from channel to channel to channel, and the volume would be exactly the same. In the digital ones, they don't have that circuitry, so that's why when you switch a digital radio, sometimes the signal is way high, and other times it's really low, and you have to adjust the volume. So don't anybody tell you that digital is always better.
There's that more on TVs and radios.
Yes, well, radio and TVs, yeah.
Right.
Well, they don't even use hardly any analog radios anymore, except unless you've rebuilt the cars, restored them specifically. They're mainly digital, but you can see it definitely in the TV, that's for sure. Of course, they do one thing. They boost the volume up every time they have ads.
Yeah, that's a big one.
That's a big one, that's correct. This is going through and looking at the circuits in a little more detail, where we're looking at it. This, of course, is the signal from the antenna. And one of the things I'm going to mention right now, have you ever heard the term you want to have essentially maximum power transfer? You ever heard that term before? What they're talking about is when you go from one stage to the next stage, you want to be able to have it very efficient, actually, and have maximum power transfer. If the impedances do not match, meaning they're equal, then you'll get a loss. And we'll explore this in a lot more detail. But what I wanted to point out to you, here's your antenna, right? It's interfacing the air, right? You know, whether you have it up on your roof. You've seen the old TV antennas, haven't you? You've seen the actual, where they have the bar and they come out longer and longer and longer. Well, it turns out air has an impedance of 377 ohms. By the way, impedance is the term that's used to describe the resistance, inductance, and capacitance. It's a general term, and we'll learn more about that at the end of today, specifically with respect to that. So if that's got 377 ohms in the air, what should the antenna's impedance be to be able to get maximum power transfer? That's correct. Now, if you ever noticed that the coaxial cable coming down from the antenna into your, like from your antenna to your TV, or the dish from the TV that you've got, is a little coaxial cable. That coaxial cable is 75 ohms, that particular one. And that 75 ohms is actually in an impedance matching circuit that converts the 377 into 75 ohms. And it goes down, and you have 75 ohms input. That's for maximum power transfer. That's the reason for it. Very important concept you should use specifically on it. You've done testing. A lot of you have been involved with testing to some degree. If you've noticed the coaxial cable that goes from the oscilloscope, RG58, is 50 ohms. So by convention, 50 ohms is the common impedance that's used in instrumentation at the higher frequencies. So that means if you hook up a 75 ohm coaxial cable to a 50 ohm system, you're going to get what they call an impedance mismatch. So these are some of the terms that you need to know. So right here, that's got that 377 that matches with what this circuit is. And this right here, this part of the circuit, see, it's a tuned circuit. You'll learn how we do that at the end of the day with the actual impedance matching circuits we'll use, or resonance circuits that we'll be using. RF amplifier. What did I tell you RF stands for?
Radio frequency.
That's right, radio frequency. That's picking up the radio frequency out of the air. Then it's going into the automatic gain control. We talked about that. But right here, what happens is we've got the mixer that combines the beat frequency oscillator with the signal coming in, and out goes 4 signals. And what are those 4 signals, guys? Original 2 plus what?
Sum
And the difference. Sum and the difference. So there's 4 frequencies out there. So we use a filter to select the one we want. We want the low frequency one. We want the difference frequency. So what happens is this low pass filter selects the difference frequency, and it just so happens these components, the capacitor, the inductor, and this are tuned in such a way that they'll pass that lower frequency and block the higher frequencies. That's the purpose of it. Also, this low-pass filter is made up of passive components. So what is this called? What kind of low-pass filter? A passive low-pass filter. Then the audio preamplifier is boosting that low frequency up as far as the audio section to get the signal higher, so you can get a much better signal-to-noise ratio. These are called active filters. And why are they active? Do you remember? Because we have an active device, the operational amplifier. The combination of the operational amplifier and these essentially filters in front of it allow it to be a sharper filter. It allows it to cut it off faster so you can get a much better frequency control. By the way, we'll go over that circuit tomorrow morning. Even though we'll be further on, that'll be part of our review to go over this circuit again. And then you've got this, essentially, the audio amplifier and speaker. Now look at this. This is an 8 ohm speaker. That 8 ohm speaker is matching this 8 ohms output impedance. You notice the taper you have on the speaker? That's 8 ohms back out here in the beginning of it. This tapering of the cone will match the 377 ohms to air. That's why it's tapered. In RF frequencies, you'll see a horn. You might have mentioned that. That horn is tapering from 377 to 50 ohms in the RF frequency specifically on that. So you've got this. By the way, we can tell what kind of amplifier is this with the plus and the minus?
operational.
That's right, an operational amplifier. This right here you'll see is an NPN. And the way you recognize the NPN versus a PNP is the arrow on an NPN is pointing outward. See how it's pointing out to that outside circle? See that? That tells you it's an NPN. Guess where the PNP is pointing? Inward. And you'll see that when we talk about transistors in more detail. It's the block diagram. We've gone over that, haven't we? Don't need to repeat that this time. This is going to show you the path of the signal. Excuse me. What happens is when the signal comes in off the antenna, it goes through that filter. And you can see it's gone out to this point here. And then it goes up through this direction, up into the mixer. The mixer combines the original signal coming off the RF with the B frequency oscillator. Okay, and then it combines, you get, how many frequencies get in the mixer, guys? Yes, 4. The original 2 frequencies, the one from the RF, the one from the B frequency oscillator, and then they mix the sum and the difference. So the sum of those 2 signals, that's the frequencies. If you had 100 and 300, the sum would be 800, wouldn't it? No, 400, right? The difference would be 200. So you have all 4 of those original there. Then the next thing that happens is you actually have it going in that direction, Then it goes through the filtering, as you see right through this. And then you go through the audio preamplifier, and then right here is where it samples part of that signal coming out. It goes out through here and combines it with this particular signal here to either increase it or decrease it depending on the strength of the signal.